All right, so by finding those limits, you can actually determine it goes down forever and ever, it goes up forever and ever, and our local, or our maxes and our mins, our extreme values, are going to be local extreme values. There's no absolute max, no absolute min. Okay, how about f prime? Maybe a little different way to write this just to make it easier to keep track of it. Let's just do them together. So for the first part, for x is greater than, or sorry, less than or equal to 1, the derivative would be negative 4x. And so that's for that function part where x is less than or equal to 1. And then the derivative of the second is 1. I don't know if we've ever written that quite like that yet. So there's our derivative. When does f prime equal 0? So is there any values in that first one that equals 0? If there's any values in that second one that equals 0. And as we look at both of those, if you get a value, make sure it's still within that domain. So if we get a value that equals 0 for the first one, well, maybe make sure that it's going to work out for that part of the domain if we go back in. Well, let's set negative 4x equal to 0. What's our solutions? That's actually an easy one to solve. You get x equals 0, right? Does that fall within the domain? Is that even part of that function? X equals 0? Sure. Is that less than or equal to 1? Yeah. But if it was actually, if we got 0 from the second function, it wouldn't matter because that's not even one of the values in that part of the function. And then if we did the same type of thing and said 1 equals 0 from that one, well, we don't get any solutions. So you're not going to get any times. There's no place where you're going to either be going up and get to that point where your slope is 0 or be coming back down. No local maxes and mins if you're not getting any tangent slopes that are 0. Whereas this one, I know at one of those two places, it has a tangent slope 0. It must be a local max. It's kind of the height or the peak of the bottom of a bowl. Any questions? You guys okay with that? Not too bad? Maybe even easier than a couple that we were doing before? I might as well find it now. So what's f of 0? F of 0. Go back and plug that into your original equation. Okay, so you've got to use that top one. So 5 minus 2 times 0 squared is just 5. And so we just need to know, is that a local min or a local max? Or maybe it's not either. Maybe it's just like kind of our x cubed where we just have a horizontal tangent. Okay, what else? F prime doesn't exist. So looking at f prime now, are there any points where f prime doesn't exist? Anything that makes negative 4x not work? Anything that makes 1 not work? No. But still, there is a point where f prime doesn't exist. F prime is your slope, right? So there's a few different situations where you don't have a derivative. What are they? Remember? A corner, a cusp, get that vertical tangent, a jump, or if it's not continuous. So one of the things we could do is we could check at that point 1. Is it even continuous? Is this even a continuous function? So if you plug in 1, 5 minus 2 times 1 squared, you get 3. 1 plus 2, that's 3. Okay, that's continuous. But what also has to be true at 1 is they have to have the same slope. So you'd also have to be able to plug in 1 into your derivative and say, yeah, they approach the same slope. It's possible that this could be still okay, that you have a point that at that 1, you get the same point on the graph. Also, when you plug in the derivative, the slope's still the same. But here, at x equals 1, we have f of 1 for both parts is good. I don't know. I really want to say that. But then at f prime, for a derivative, we get 2 different values. So I could say f prime well, obviously we're looking at where it doesn't exist. So it doesn't exist. But I'm thinking, like, how do we want to write that, or how do I want to say that for your notes, just so that when you're going back later, maybe if I gave you the little piece of the graph, what this actually looks like. We have a parabola opening down, and then we have a line. And so I could say the slopes are different from the left and the right. or you could say the slopes approach something different from the left to the right. I'm trying to think what would probably be the best or help you remember that, or if you went back, or maybe there's something that you, like what I said, that kind of, oh yeah, that makes sense to me. You could write that down. But something to know, why does it work at x equal 1? Slopes are different from the left and from the right, what that limit is approaching, or what the f of x value, or f prime of x value gives us. So we end up with 2 points. We could also find f of 1 right now if we wanted to. It won't take very long. Which function are we plugging f of 1 into? The top one. X is less than or equal to 1, so 5 minus 1 squared is 1, 2. 5 minus 2 would be 3. How do you tell if we have local maxes or local mins? Well, if we didn't know it was absolute max, we could actually have a couple local maxes. That's possible, but you'd probably also have to have a local min. I'll give you, you don't have to write this down, but you could have a local max and then a local min and then another local max. That can happen, but you can't really have 2 local maxes if you're not going back down to get that local min. So we're probably going to have one of each or just one. How did we do it last time? And the examples you guys asked today from the homework. Oh, I know some of you guys know. Just say it, and then we can move on. How do we know if they're local max or they're local min without just going to your calculator? Table. You can make a table, plug in some values. You really want to know, is it bigger on either side? So maybe we'll pick some values. Kind of spell it out in our homework by doing smaller, bigger. We could do that there if you want me to. But really what I'm looking at is, I know that at 0 it equals 5. So we're looking at that one, local max or min. And I know at 1, you end up with 3. So what about points around that? So maybe we're going to have to check like 0.5. Or maybe we'll have to check like -1 or 2. And that 1 is kind of tricky because when you go back in, depending on which point you check, bigger or smaller, you've got 2 different ones to plug it into. So just make sure you plug it into the right one. Can't see that. I guess I have it here. Plug in -1, what do we get? That's got to go into the top one. Still get 3. That's smaller. And I know that since we checked those limits at the beginning, means the other side's going to end up being smaller, but we can do that. 0.5 squared, that's a half. If you square that, it'd be a fourth. A fourth of 2 would be a half. 5 minus a half. Bust out your calculator and check me, but I think we're getting like 4.5 or something like that. And it looks like we may end up with, well, definitely local max, but maybe the other one's a local min, so check 2. You still got to go back and plug 2 in. However, what's tricky here is you've got a different equation to plug it into. What'd you do, computer? Hold on. Okay, so you plug that back into the other one. You get 4. Okay, so maybe that is a local min. But it didn't necessarily have to be, because that second function was going to be different, so it didn't necessarily have to give us that. And I'll say that we've got a local max at 0. Now I could have said what it is. Maybe I'll say that for the local min then. The local min, I could even tell you, is 3. And that's when or at x equals 1. Any question? And just another one to work through, see what types of things you're looking for, what the derivative is showing us, and why we're doing it equal to 0 when it doesn't exist. Hayden, you good with that? All right, one more. This will go pretty quick. Question? Sure. Del, you just stretching? I'll tell my study hall student that did the seating chart that you approved.
I know. This one sucks, man.
All right. Example. Graphical method. So pull out your graphing calculator, see if you can get that plugged in. All right. So here's what it is. Again, you guys that got that, feel free to go on ahead. I'll even write this down. If you want to get this in your calculator correct, well, depending on which calculator you have, but if you've got one similar to the TI-84, you guys, if you're still working on that, you need to, Alex, I know that you're working with a couple kids, but if you're going to do that, you need to do it really quietly now. So I can, now that we're gonna look at this together, I need to everyone be able to hear, follow along. You need the natural log of the absolute value. So you need some parentheses going on here. So sometimes I'll even write it down before I put it in my calculator. I'll write it down or write it out with the parentheses so I can make sure I get them all in the right place in case I can't see that. But I need the natural log of the absolute value of, and then if you're not sure, you do need to have the bottom part in parentheses so it divides the whole thing. But the top part doesn't necessarily have to be. So you could do x divided by, but then again that whole bottom would have to be in parentheses so you divide the whole thing. If you don't put that in parentheses, it'll follow the order of operations and it'll just say x divided by 1. What's x divided by 1? You guys. So what would x divided by 1 be? It'd just be x, and then you'd have x plus x squared. So it's important that when you are putting that in your calculator that you know how to group that. The 1 plus x squared needs to be grouped together so the whole thing's divided. That closes the absolute value. That closes the natural log. So when you're plugging in your calculator, if you're having troubles or it says like domain error or I think it would say syntax error, you're going to have to go back or dimension. I don't know what it say. Anybody get that error? You guys are all pro. You get that plugged in. Get our window. End up with a graph something like this. And we're looking for those 2 points right at the top where we can say, okay, that's as high as it gets. And where does that happen? It does say, now read the directions, find your extreme values. So the first one we did in this section of notes said, where is your extreme value? Or where do you have a local max or min? Well, that was the x value. So x equaled -1 and x equals 1 would be end up being our answer here. But that's not what they're asking. So here it's asking for the extreme values, which is how high does it actually get? How low does it actually get? And you'd go to second, calculate max. If you can get that in your calculator, you put your left bound. You're going to have to do it a couple times. And again, you'd end up with a couple local maxes. You have a local max at -1. But again, what's your extreme value? -0.69 is what they're asking for. And then you've got another local max at 1. And that's positive 0.69. And so the question is that an absolute max? So could it be equal to those values? Oh yeah, it's still negative. Thank you. If we went back in our notes, by definition, what does it mean to be an absolute max? Or what would it mean to be a local max? And so could it be equal to the ones around it? I'm turning back in the notes. We've got local extremes and we've got absolute. So let's go back and just look at this really quick. Let's scroll back here all the way to the very beginning. Absolute extreme values. So what is defining an absolute extreme? If and only if it's, what does it say? Greater than all the other values in the domain. So if I focus in here, by definition, to be an absolute max, it needs to be greater than or equal to all the other values. So what are those values there? Are they absolute max or absolute min? It seems to suggest in our definition of what an absolute maximum value is that you could have it equal to another value. So we have those two local max. Are they absolute max values? Yeah, according to definition, they're actually both absolute max values as well. Locally, they're a max, but as a whole, you also have that as a max because it says to be that or to satisfy those conditions or equal to. Cool? So that's kind of how you'd go if you weren't certain. Like, would this be that? Well, go back to your definition and see what are my requirements. Any other questions? Yeah, you want to go back to that problem? Okay, so how about any other questions from this one? I didn't really show much work there. So maybe the hardest part of that's getting your window so you can see it the best. Or, knowing that it goes on forever and ever, down forever and ever, or checking your table. Going once.